Well, hi, everybody. It's great to be here. I've been looking forward to this for a long time. Although I was asked to write about, or to talk about grand challenges at the interface of water and climate, and maybe like many of you, I've spent the last 2 days completely rewriting my talk. Originally, it was an AGU science talk, and then it was a talk about communications, and then, I'm not actually sure which version you're going to get. So let me start at the end with my conclusions. Water is a big topic, and to some degree this is a little bit of a transition from a Group 1 IPCC talk to a Working Group 2. I'm convinced climate's changing. I think most of you, all of you are convinced climate's changing. I don't have to reiterate that. What I care about is what the implications are going to be for things that we, society, cares about: food and water and human health and ecosystems and the consequences of a changing climate, and what those consequences are going to be and what we ought to be thinking about preparing for. In order to understand these things, I think we have to improve science and data, more science and better data, and more data and better science. We have to understand the water balance better. It's sort of remarkable the gaps in our understanding at the global level and at the regional level about the water balance. And that's partly a data problem. It's not necessarily a science problem. We need to improve our ability to model hydrologic processes and to forecast. But maybe more importantly than all of that, we need to improve our ability to manage complex water systems that provide society with the goods and services and the water that we want, in particular under changing conditions. And I would like to argue that it's difficult enough to deal with water challenges now in the absence of climate change. But in addition, we're going to have to impose on our institutions, on our systems, on our understanding future climate changes or ongoing present climate changes. So the grand challenge at the intersection of climate and water is not purely a scientific one. And this is, if you take anything away from my talk, take that. The challenges for water are largely economic and social and cultural and institutional. And imposed on top of that are going to be these hydrologic changes from climate. All right, so I could stop there, but I don't have to. The reality is water is connected to everything we care about. It's connected to public health, to ecosystems, to the energy systems that we use, to forestry, to agriculture. Without water, we are not going to be able to feed the 7 billion people on the planet and then the 8 and 9 billion people that are coming. Infrastructure and the debates about the kinds of infrastructure we want to repair and manage in the developed world or build in the developing world are all related to water. So one could get into the water problem from any of these different aspects, or conversely, if you're interested in water, you often have to deal with all of these integrated aspects, and that's another part of the challenge in the water sector. So even without climate change, we have serious challenges associated with water. So before I talk about climate change, I have one slide to tell you about the problems for water without climate change. The first is that there are billions of people, it's the 21st century, there are billions of people today without access to safe drinking water and adequate sanitation services. And in my opinion, that's the biggest problem in the water world, the failure to meet basic human needs for water and adequate sanitation. And that leads to bad things: cholera, dysentery, water-related diseases, 2 million preventable deaths a year, mostly children under the age of 5. We have deteriorating natural ecosystems that depend on the water that we humans also want to use for what we do with water, that are suffering because we take water out of those systems. Deteriorating infrastructure and the lack of investment, little public awareness about the nature of water problems, ongoing disputes and violence over water. We do a lot of work at the Pacific Institute on conflicts over water resources going back 5,000 years. If you're interested in history, we maintain something called the Water Conflict Chronology. Google it. There's a great, disturbing history of water violence associated with water resources over the past history. We have few coherent international water policies to deal with these problems, and I would argue we have few coherent national water policies to deal with these problems. And last year, we published a book with Oxford University Press called A 21st Century U.S. Water Policy, talking about some of those issues at the national level. But I would also note that in many ways, we have global water challenges, we have national water challenges, but often, primarily, water is a local problem. And that's another part of the difficulty of dealing with water. There's a spatial problem of scale and a temporal problem of scale, but we don't deal with that adequately. Also, the climate cycle is the hydrologic cycle. And again, this is key to all of the things that you're trying to deal with as well. So you remember this from second grade. I downloaded this morning. This is a slide from a second grade, and note social studies, and don't get me talking about national education problems with the sciences. This is in the social studies curriculum. So the hydrologic cycle in second grade that you all remember, here it is. And notice the words evaporation and precipitation and condensation and sublimation. That's not on here. That's not for second graders. The sun heats the water, and the water vapor goes up, and it makes clouds, and wind moves the clouds, and it rains, or it snows, and it runs off back into the oceans. Okay, that's the hydrologic cycle, right? That's the climate cycle, too. Now, the USGS has a little more sophisticated version of this, and there are even worse ones. There was one, Kevin Trenberth. I almost put Kevin's up. So that's the hydrologic cycle, and it's the climate cycle. As we change the climate, every aspect of this is going to be affected. So climate change poses very real threats to natural hydrologic systems, but it also poses threats to the very extensive, significant infrastructure that we've built to manage the hydrologic cycle. And it's not just that climate change poses these threats. I'm going to argue that the threats are already manifesting themselves, and we see evidence of this as well. And I'm going to go through some of this fairly quickly, because many of you have seen this. In fact, many of you are responsible for this. But to give you a sense of what we understand about this already, we can look at the historical record of precipitation patterns over any particular region. This is the United States from 1959 to 2008, showing regional changes in precipitation patterns. I'm not suggesting necessarily these are climate change induced, but over time, there's natural variability, of course, enormous natural variability, especially in precipitation. But we're seeing changes in precipitation patterns. Whoops. And this is sort of annual averages. If you look at extreme events, short-term rainfall patterns, you also see changes over time. Projections of precipitation changes, and again, you've heard over and over again already, and you know climate models are especially not great at regional, small-scale precipitation changes, but they're getting better, and we can get a sense by looking at models, by looking at probabilistic combinations of model projections of potential changes in precipitation patterns moving forward. And unfortunately, at the moment, whether you believe it or not, the climate models are suggesting, generally, that wet areas will get wetter and dry areas will get drier. Not always, not everywhere, and that's the way the world delivers moisture around the planet. It delivers moisture to what are wet places and doesn't deliver moisture to dry places, and it looks like that is going to be emphasized, exacerbated in climate changes. And so we see the Southwest United States, already a dry area, and I would note the scale is inches. It's not changes in percentage. It's not percentage changes. Those would be even greater. So we don't really want the Southwest to get drier. We already have very significant problems in that region. And so this is the kind of information we need to know moving forward. Combined, I didn't show the evaporation changes, but if you were to look at changes in projected runoff, which is a combination of evaporation, precipitation patterns, and other factors as well, again, it shows very significant decreases. And the hatched areas here suggest a little more confidence in the models than unhatched areas. Show the Southwest and California and the Great Basin and the Colorado Basin, where you're sitting right now, are going to get drier. And that's not what we want from a water management perspective. Snowmelt will occur earlier. This is partly what some of my early research suggested, looking at the Sierra Nevadas. We didn't have a good sense of what's going to happen with precipitation, but we know it's going to get warmer and is getting warmer. And when it gets warmer, snowmelt-driven basins have a greater ratio of rain to snow. They have faster and earlier runoff of what does fall as snow, and you have higher winter flows and lower spring flows, and that's a risk moving forward for the hydrologic system and for the managed system as well. And in fact, if we look at trends in snowpack and snowmelt, typically April 1st snowpack is a measurement used to measure what the status of snowpack is in the mountains in the west. We see trends that suggest, especially in lower elevation snow areas, decreasing snowpack in the spring. And that's some evidence already in some people's minds that we're beginning to see changes in the hydrologic system. That will lead to changes in the timing of runoff. Maybe the annual average stays the same, and what we simply get is a change in seasonal timing. And that's what this suggests, a change in the peak timing of stream flow from the big red circles are more than 35 days earlier, an advance of more than a month in peak timing of runoff. What this means is winter flows get higher, spring and summer flows get lower. And in the West, I'll tell you, we don't want winter flows to get higher. That's the flood season. And we don't want spring and summer flows to drop, because that's when the agricultural irrigation demands start to go up. But this isn't just a question of hydrology. It doesn't just matter if the climate changes. What matters, in addition, is population growth moving forward, demand for water moving forward, the infrastructure that we build. So climate change is going to be imposed not just for water, but for agriculture, for human health, for all of the things that we care about, on top of a human dynamic system. Is this now? This advances without me even touching it. So this is projections of changes in population by county for the year 2000 to 2050. And again, look, it's suggesting biggest increases in population growth in areas that happen to be dry, the Southwest. So why do people move to hot, dry areas? Well, partly because Minnesota's cold in the winter and people don't like to live there. And partly because the assumption has always been that it doesn't matter if there's no water. You move to the city and they'll provide the water. The assumption has always been we'll provide whatever resources we demand if you move somewhere. And that's historically been pretty accurate. But is that going to be accurate moving forward? Okay, so you put all these things together, changes in climate, changes in population projections, changes in demand for water. There are lots of ways of measuring stress. There are lots of different kinds of indicators you can look at. This is just one. This is the ratio of runoff to water use in a region. That's sort of natural variability, natural water availability to a measure of demand for water. And it suggests what one might have assumed even if one hadn't done any modeling at all, which is that the western United States, as an example, is going to be under far greater stress in the future than other parts of the United States. And people do this for regions around the world. Boy, is this sensitive. So some thoughts about data. We don't know what we need to know, partly. We always want more. Talk to a hydrologist and they want more data. And we don't use what we have very well. So this was already mentioned in Laurie's talk in the Arctic. We're losing monitoring stations in the Arctic. This is a graph that shows historical discharge data collection. This is the Global Runoff Data Center in Koblenz, Germany. This is stations that collect monthly data, stations that collect daily data, and time from 1910 up to 2010. And so you can see we're starting to lose over time data collecting stations for runoff. That's a financial issue. It's not going to be satisfied by satellite measurements. We don't collect good runoff data at the moment from satellites, so we're losing ground data. We also don't know where we're going. So this is a graph I like to show. The blue line here is roughly actual global withdrawals of water worldwide. The little dots, The red dots are projections of future water withdrawals that were made before 1980, when hydrologists tried to project future demand for water. The little blue dots right here are projections made between 80 and 95, and then the green dots are projections made after 1995. And one of the things that suggests is before 1980, the assumption was demand for water was going to continue to be exponential, like population, like GNP. This is what I was told as a hydrologist. Population goes up, GNP goes up, demand for water goes up, of course. It always has, it always will, and at an increasing rate. And then after that, now some of the more modern projections are, well, maybe that's not necessarily the case. Maybe we're reaching peak water. Maybe efficiency measures can cut demand for water. There are a lot of things going on here, and I don't have time to describe them now. But the difference between this amount of water and this amount of water is huge. The truth is, we couldn't find the upper amount of water. We're tapped out increasingly. But we don't know where we're going. And that's a big uncertainty. And then there's data error and misuse. And I'll let you just read that. Okay, so I don't know whether some city planner had a sense of humor and all of the other city planners were mathematically challenged. But of course, we have problems with data collection and use all the time. Now, there's some good data news. We're starting to collect new data. This is GRACE satellite data that shows that GRACE measures to some degree changes in gravity, which to some degree can be correlated to changes in groundwater availability. This shows for India over some period of time very substantial increases in gravity that basically represent massive increases in soil moisture during the monsoon season, and enormous decreases in groundwater in northern India from massive overpumping. So we knew there was overpumping in India and other places. We're beginning to get a better sense of that without having to measure individual groundwater wells. There are other ways of looking at water availability. This is a world mapper for those of you the proportion of the area of the country is a reflection of the proportion of worldwide freshwater resources found there. So Brazil, the Amazon, Peru, the Amazon basin, where most of the water is. Africa's a problem. And you can see it if you look at data in this kind of representation, this kind of visualization. So there is a grand modeling challenge also. We need a new generation of models that can exploit advances in computing power and improved access to data. We need improved hydrologic representations at a higher spatial and temporal resolution. We need improved surface and subsurface dynamics for water. We need land, ocean, atmosphere, cryosphere interactions represented better in these new models. But in addition, a grand modeling challenge also means we have to integrate the human component here. Dams, groundwater extraction, withdrawals and recharge, alterations of nutrient flows, urbanization, and much more. And we're beginning to move forward in this area. There is an example of a modeling attempt to do some of this, and Eric Wood at Princeton has written about this, and I've written about this a little bit in a paper that's coming out. But we also need better model integration. So some of you work at the GCM level, some of you downscale to the watershed level, some of you are interested in runoff and flooding, but we also need to integrate utility systems and hydropower into this debate. Water supply and agricultural production, land use planning and resource use, and that's a challenge. We also have to understand extreme events. There hasn't been much talk about this yet, but there will be. This is atmospheric rivers. This is a satellite photo of atmospheric river hitting the west coast of California. That's where most of our water comes in the winter. It comes in these short-term events. Same thing, the extent and frequency of storm events. In the western United States, storm events that come off the Pacific that we don't fully understand. And then this is sort of the Main Street, Wall Street slide that I have. This is the Mississippi Basin in the year 2000. This was a 1 in a 500-year flood event on the Mississippi River. There was another 1 in a 500-year flood event in 1993 on the Mississippi River. Now, we might not have another one for 1,000 years, and statisticians would be happy. But this makes statisticians nervous and hydrologists nervous. And you all know that the statistics of extreme events are changing. Let me put it that way. We also need a better understanding of different kinds of connections. This is a graph that correlates the dynamics of cholera in Bangladesh with sea surface temperatures lagged from ENSO. It turns out cholera in Bangladesh is a function of sea surface temperature. And cholera is a bad thing from the water community's perspective. It's an incredible killer of people. This is from 1912, just as we were on the verge of implementing water systems in the United States that got rid of cholera, because we implemented chlorination and filtration, and we eliminated cholera in the United States, but not everywhere. And this is a graph that shows cases of cholera reported to the World Health Organization from 1949 to 2011. And I'll tell you right now, only half of all the cholera cases worldwide are actually reported, because some countries don't classify acute diarrheal disease as cholera. They classify it as acute diarrheal disease, and they don't report it as cholera. But we have a very serious unresolved problem with cholera still. Finally, I'll just conclude. The implications of climate change for water will depend on the complex realities of water around the world. And it's a complex, integrated issue, and it's not just a science issue. We're not going to solve it building new reservoirs. Global reservoir storage is leveling off. We've built on all the good reservoir systems and the big rivers, and we'll still build a few more, but it's not going back to an exponential curve. Irrigation and food is a key part of this. How do we grow more food with less water worldwide? And what's the implication of higher temperatures going to be on water demand for agriculture? We have a regulation in the United States. Shower heads can't be more than 2.5 gallons of flow per minute. The regulation doesn't say anything about the number of shower heads you install in your home. I took this picture. I'm not going to tell you where. But it's not my house, I'll tell you that. And finally, total water use in the United States has leveled off. We use less water in the United States today for everything than we used 35 years ago. And this is a radical change in thinking. We've gotten off of this exponential growth curve, and I won't talk about now why, but this is a dramatic change in the world of water. So, as goes the climate, so goes the water. Water is central to human development and ecosystem health, but we already fail to manage water adequately. We're increasingly manipulating the hydrologic cycle in a lot of ways, including, but not exclusively, through climate change. We have to improve our observational networks and data, our scientific understanding, our modeling tools, and we need to cultivate a new generation of water experts that take a broader view than the historical engineering infrastructure perspective than we've taken in the past. Thank you very much.